Okay. So, good morning to one and all. So, let us continue with our discussion with regard to analog modulation techniques. So, as we were discussing since last class, we were just trying to understand what is an AM signal and how is an AM signal is generated, particularly the modulation of AM signal. And then we also identified that AM signal consists of carrier signal and two side bands. Okay. So, it is a very interesting logic there. So, whenever you try to take a modulating data, that is your message, and you are trying to multiply it with your carrier, so you automatically generate an AM signal that consists of two side bands, and to ensure that you also have the carrier along with it, you add carrier to that signal, and a carrier along with these two side bands are transmitted to the base station, from the base station. So, at the receiver, what you do is you try to take this data and then start identifying what will be the amount of message that is available in the received carrier signal. And we also identified that the modulation depth for an AM signal is a very important parameter which defines Vm by Vdc. We also identified that there are three modulation depth parameters like m less than 1, m equal to 1 and m greater than 1. And we also derived an expression for the total amount of power that is required for transmitting an AM signal. That is, the total power is equal to the carrier power multiplied by 1 plus m square by 2, where m is basically the modulation depth. So, these are the three important factors that we could really discuss in the last class. Okay. So, what we will do today is, let us understand. Suppose if at all you try to take an amplitude modulated signal and it is now being transmitted. Once it is transmitted, it is available on the channel, and once it is available on the channel, there will be lots of noise coming into the signal that is being received. So, the channel consists of multiple data. So, channel will have not only our signal, but also it will have multiple other signals which is also available in the channel. All these signals are now going to reach the receiver. Once these signals are going to reach the receiver, it is the most challenging task for the receiver to exactly extract or recognize the carrier in which it is being tuned to, and from that carrier, how do you get back the message that is being used for modulation. So, we need to now understand what are the modulation schemes that are available, using which we can start extracting the carrier signal from the channel, and correspondingly now we can extract the carrier signal from the channel, and from the carrier signal we need to extract the message from the data. Now, to do this process, there are two very interesting techniques that have been identified by researchers, and the two different techniques are named as, one is called as envelope detection technique, or we also call it as non-coherent technique. And the second important technique that is used is synchronized or coherent demodulation technique. Now, these two techniques has been invented by people like us, or people the scientists long back. And now it is a very interesting circuit that they have used to extract the message from the modulated data. Now, let us understand what is this envelope detector and what is this synchronized detection, or we also call it as coherent demodulation technique. Okay. Yes. Now, let us very quickly understand what will be the circuit that are required, or what is the component that are available in the circuit to perform demodulation process. If you see the circuit, whatever you come across here, this circuit basically consists of a diode. Okay, it's a very interesting device. A diode, we all know that it's a switch. So, if at all you apply a voltage to the input at the anode, the diode is forward biased if the voltage is greater than the cut-in voltage of a diode. And then once the the input is more than the cut-in voltage, the switch basically closes. So, input will be now equal to output. Suppose if the input voltage is less than the given cut-in voltage, the diode will be switched off. That means the switch is open circuited, so output will be actually 0. Then we also have a resistor which is connected in series to the diode, plus we also have a capacitor which is connected in parallel to the resistor. Now these are the three important components that people have identified that could help us in extracting the message from the received carrier signal. Okay, now let us see how does this circuit actually work. So what we do at the receiver is, so there are three important components. Let us summarize it. In an envelope detector, we are trying to have three components like the diode, resistor and the capacitor. All of them have been connected according to the circuit that is provided over here to make sure that we extract the message from the incoming modulated signal. So we know that the incoming modulated signal is actually given represented by this waveform. So this is how an AM signal is actually represented, and we are also assuming that the modulation index or the modulation depth is now going to be less than or equal to 1. Since it is going to be less than or equal to 1, it is always going to be a double sideband signal. Now this signal, what is being received at the receiver, is now applied as an input to the envelope detector. Whenever this input that is coming from this incoming signal is applied to the input of an envelope detector, we apply with respect to these two terminals. One is the plus and the other one is the minus. Since we are applying it with respect to these two terminals, we know that this point is always a ground point. Now what happens, the signal when we apply across these two terminals, the diode will be now triggered, and when the diode is triggered, what will the diode do now? It is a switch, it is a basic switch. So what will the diode do now? The diode will now try to understand what is the signal strength. That means what will be the amplitude of the signal that is available at the input. Suppose if at all you are having a signal, and suppose if your diode cut-in voltage is equal to 0.6 volts, this is your signal, and then this is a 0 level, and then this is 0.6 volts. That is the cut-in voltage of a diode. Suppose if at all you take this diode having a cut-in voltage of 0.6 volts, suppose if your input signal is less than this, the diode will be switched off. That means the diode will be an open circuit device. Since it is going to be an open circuit device, your input will not go through the diode. So there will be no output available across the diode. Suppose if your input voltage is anything greater than this, what will the diode do now? So because the input voltage is greater than the cut-in voltage, the diode will be switched on. Because the diode is going to be switched on, the output of across the diode, the output that is going to come out of diode would be basically the positive voltage. Suppose if you apply a negative voltage across the diode, a negative voltage across the diode, if it is applied, so what happens, because this negative voltage is less than the threshold, that is the cut-in voltage of the diode will be switched off. Because it is going to be switched off, the output will be again equal to 0. So if you try to understand, okay, in a simple circuit whatever we have discussed here, okay, so the diode plays a very important role in envelope detector, because the diode is now made to work as a switch, and it is going to be switched on or it is going to be switched off, and the switching on and switching off of a diode is controlled by your input signal, and that is your AM signal. If the input voltage that your AM signal is above, it is having a voltage above the cut-in voltage of a diode, the diode is on. If it is below than cut-in voltage, the diode will be switched off. So based on this logic, if you try to see this picture that you come across here, okay, wherein we try to take an input signal and it is applied to a diode. Now the diode works as a rectifier, wherein it is trying to remove all the negative portions of this signal, and only the positive portions of the signal are made available at the output. This positive signal that is available at the output, we know that there is one sideband available on the positive data. So let us understand why is this very important for us. Since we are talking about a modulation index of equal to 1 or less than 1, it is always going to be a double sideband signal, wherein you have one sideband on the top envelope, the other sideband on the bottom envelope. Since there are two sidebands available, it is more than enough for us to have only one sideband, and using that one sideband information, you can extract data from the incoming carrier signal. So what will the diode now do? Because the diode is working as a rectifier, what it will do actually is, whenever the signal is applied, it will cut off all the signals on the bottom side, because they are all less than the cut-in voltage of the diode. Because they are all less than the cut-in voltage of the diode, all the positive data available here is available at the output of the diode. And now if you try to see the positive voltage, whatever you come across, they are all like pulses now. They are all like pulses like this. And if you try to take these pulses like this, okay, they are all the pulses, because it is a carrier signal which is actually a sine wave. So only the positive half of the sine wave is basically taken out of the diode, and you get all these pulses like this. Now we call it as envelope detector, because if at all you keep tracking the envelope of this signal. What in the envelope? The peak amplitudes of all the signal. These peak amplitudes we call them as envelopes. So that is why we call it as envelope detector. Okay. So let us once again understand what is the importance of a diode there. So the importance of a diode is it is acting as a switch, and it is able to work as open and close action, and it is going to be closed whenever the input voltage is going to be greater than the cut-in voltage of diode, and it is basically going to be off if the input voltage is less than the cut-in voltage of the diode. Since your carrier signal is going to have both positive half as well as negative half, only the positive half is actually obtained at the output of a diode. Now if you try to take the positive voltage available at the output of the diode, now what is going to be done by these two components over there, the resistor and the capacitor components? The resistor and the capacitor component that are available over there, they are now trying to take the data coming out of a diode, and then they are trying to identify what would be the envelope that is available across the capacitor. This is what we get at the output of a capacitor now. How are we going to get this information? So the process is, suppose if the first peak is this, second peak is this, the third peak is this. So what will happen? Because you have a capacitor over there, and this capacitor is initially said to be completely discharged, it is having 0 voltage available across it. So whenever you apply a positive peak, this capacitor will get charged. It will just charge to the positive peak. Once the capacitor is going to get charged, let me change the colors here. So the capacitor is now going to charge. Once the capacitor is going to charge, what will happen now? After the capacitor is going to charge the peak value of the first pulse, there is a gap available here between the first and the second pulse. Because there is a gap available between the first and the second pulse, what will happen is the capacitor will now try to start discharging through the resistor. Because it is trying to discharge through the resistor, so what will happen? This voltage that is being available across the capacitor will slightly discharge. Before it could completely discharge, what is happening now? The second peak is available from the second set of the carrier. Because the second peak is available, what will happen to the capacitor now? It will further discharge to a small extent and again charge the second peak, and it will again be there. Suppose if there is again a space available between the second and the third pulse, the capacitor will try to slowly discharge, and again what happens is the third peak occurs. So what will happen? The capacitor will again try to discharge. Now if this is going to happen, if you try to track all the charging points of the capacitor, the charging points of the capacitor, you find that the first pulse was here, second pulse was here, the third pulse was here. The capacitor is now trying to charge, discharge, charge, discharge. It is charged. It has now reached the envelope. So now if you try to see, it is approximately like an envelope. Suppose what happens, the fourth pulse is basically like this. So if you do not if the fourth pulse is like this, what should the capacitor now do? It has to slowly discharge. So if it is taking more time to discharge, then you may not be able to actually capture the envelope that is actually expected. So what is actually done is, to ensure that the capacitor is now going to discharge faster, whenever a pulse occurs like this, we are introducing a resistor over there. The presence of a resistor ensures that you are able to charge to the peak as well as you are able to discharge quicker, so that you will be able to easily track the envelope of the amplitude modulated data. And that is the reason why we have both a capacitor as well as a resistor. So let me summarize this. It's a very interesting circuit that is available for getting the message from an amplitude modulated signal. So the process is, let us quickly summarize this. So the AM signal will have two sidebands, the positive sideband and the upper sideband and the lower sideband. So because the information is available both in the upper sideband as well as the lower sideband, so the diode will now, what it will try to do is, it will extract the information only from the upper sideband. So you are able to take the data from the upper sideband. So if you try to take the data from the upper sideband, because the diode is now working as a rectifier. Since the diode is working as a rectifier, the data that is available on the upper sideband, if at all you would like to extract the envelope, which is actually the message, what we now do is, we are actually giving it to a RC combination circuit. So what will the capacitor try to do? The capacitor will try to charge to all the peaks, and the resistor will ensure that it is going to discharge accordingly, and you will be able to maintain you will be able to capture the envelope of the given signal. So if you see, the actual envelope was actually like this, but we are now getting a distorted envelope. Since it is going to be distorted envelope, this distortion is achieved because of the charging and discharging action of your capacitor and resistor. So what is actually happening? The capacitor and discharge, it is going to charge across the resistor, and that is why we are able to have all these distortions. If at all you would like to further remove that distortions, you can take this data again and give it to a low pass filter further, so that you will be able to further smoothen the output, and that output will be approximately equivalent to the amplitude signal that was used for modulating your carrier. And that is what the working principle of envelope detector is. Okay. So now let us go to the next important circuit. Okay. Yes. So as I was trying to mention that there are two kinds of detectors that will be available, that we are going to discuss: the envelope detector and the synchronous detector. Now whatever we discussed right now is basically the concept of envelope detection. So as I was mentioning, if your input signal, let us assume that your input signal, okay, let us assume that your input signal is basically having a peak like this, okay, and this is with respect to 0 volts. If your cut-in voltage is this, threshold voltage is 0.6, this is your 0.6 is cut-in voltage. If at all your input voltage is basically going to be greater than cut-in voltage, the diode is working as a rectifier, you will get this voltage at the output. And if you are having this input available at the data, assume that let me redraw it, sorry. If your input is this, and the cut-in voltage of a diode is set to this, so what happens? The top portion, whatever we are able to get, will be rectified, and it will be available at the output of a diode. All these portions, whatever is below the cut-in voltage, will be removed by the diode. Suppose if your input voltage, if the input voltage is very small, it's very small like this. If your input voltage is very small in this case, how will the envelope detector work? In such cases, what is being done is we use the square law model or the square law property of a diode. Let us understand what is the square law property of a diode. According to the square law detector module, the same circuit whatever we discussed previously is also used as square law demodulator. In the square law demodulator, what happens basically is, we know that there is a linear relationship between voltage and current of a diode. According to the graph whatever we see here, if the voltage across the diode is increased, if you are trying to increase voltage across the diode, sorry, yeah. Okay. So if at all we try to increase the voltage across the diode, the voltage is slowly increased. As we keep increasing the voltage, we find that the current also increases across the diode. This is the graph what we get. If you try to see the graph here, there is a variation between voltage and current. And if you try to see the variations here, the total variations of at all you try to track, there is a non-linear relationship between voltage and current, because here it may be linear, again it is exponentially varying, again it is going to vary in a different slope. Because of the variations in the slope between the voltage and current, we call a diode as a non-linear device. If at all we consider the non-linear property of a diode, according to the non-linear property of a diode, it is found that if the voltage basically increases and this voltage is now trying to change the current across a diode, the relationship between the voltage and current is found to be I of t is AV plus BV square and plus CV cube. So there is a small, no, it's a V square and V cube. So this property is called as the square law property of a diode. So what is actually happening here is the current that is available across a diode is going to have a relationship between the voltage, and they are related by the simple expression which is going to be AV, where V is voltage, A is a constant, B is a constant, V square again V is a voltage, C is a constant, again V cube is a voltage, or V is a voltage. So if at all you try to understand the square law property of a diode, according to square law property of the diode, a variation in the voltage leads to an exponential variation in the current, and that relationship is given by this particular equation. By using this property, let us now understand how can a diode be used to extract the information from the given signal. Now we know that in an amplitude modulated data, the signal is represented by VDC, which is the DC voltage, plus M of t, which is the modulating data, and all these are now multiplied by carrier, that is going to be cos of omega ct, and this is the modulated data that is now available in the channel. If this signal is now received and this voltage is applied across an AM detector, okay, that is your demodulator, what is going to happen now? Let us see the concepts here and how are these going to change. Yes, let us take the equations here. The voltage is now given by the current across the diode is given by AV plus BV square plus CV cube. We know that V is VDC plus M of t into cos of omega ct. Substituting this equation here for all the V actually here, okay, so it is V square plus V cube. By substituting it, we find that, okay, we get an expression like this, which consists of, by now solving this expression, we find that it is AVDC plus AM of t cos of omega ct plus B into VDC square plus 2 VDC M of t plus M of t whole square into cos square omega ct, and so on. Further, by simplifying all these three equations, we come across the final expression, which is actually, this is the final expression now. In this final expression, we find that, okay, if at all you try to substitute the AM signal in the current expression, we find that there are multiple components available in the given signal. These multiple components are, one is a DC signal, which is actually scaled by a constant called A. The second term, whatever you find here, is M of t into cos of omega ct, again, which is the modulated data, which is like an AM signal, but only difference is the modulating data is now multiplied by a constant called A. The third component is again a DC signal, which is VDC square by 2. The fourth component is VDC into M of t by 2, and the fifth component is M of t whole square by 2, and the sixth component is VDC square by 2 into cos of 2 times omega ct. If you try to take all these components, out of all these components, the most important components for us, which is containing the message, is this data, wherein you have only M of t whole square by 2, that is one of the input data that is going to be required for us, plus this next component where we come across 2b VDC into M of t by 2. Now these two components are basically important because they do not have a carrier along with this modulating signal M of t. Because there is no carrier available within the with these signals, we have to see how do we extract these two data. Now let us understand, out of these two signals, the first term that we have taken over here, this information is M of t multiplied by VDC multiplied by 2b, and they are all divided by 2. So if you try to see, it is M of t multiplied by b into VDC. That means your modulating signal is now scaled by a parameter b VDC. Second term, whatever you come across over here, what is happening is it is M of t whole square. So we know that it is M of t whole square, and let us understand whether this signal is required for us, because both these terms, whatever we come across here, do not have carrier. But what is happening in the second term over here, because it is M of t whole square, we know that, okay, either it is cos square M of t or cos square omega mt or sin square omega mt. Cos square omega mt will be now equal to 1 plus cos 2 omega mt by 2. So what happens? The frequency will be multiplied by 2. So what happens? The frequency is lost if at all you take these components. So what I mean basically is, if you try to have m of t, and this is m of t is equal to cos of omega mt, and if you take square of this, the square of this will now give rise to cos of 2 omega mt. So whenever you take this component cos of 2 omega mt, what happens basically is the frequency is now multiplied by 2. So what happens? The modulating signal will be scaled by a frequency of 2. It will be translated by a frequency of 2. So what happens? This component is not required for us. Even if it doesn't have a carrier signal along with it, because we are squaring the signal there, what happens? The modulating signal, that is m of t, the frequency of that is translated by 2. So we don't need this component. So the only component that we need to extract is m of t, that is this component. Why? Because it is having m of t plus the magnitude of m of t scaled by b times VDC. So what we do is, to extract this data from the output of your diode, what we do is we take the information of from the diode and give it to a low pass filter. So what is actually done is, once you take the once we apply an input to an diode, so because the relationship between voltage and current is non-linear and they are related by a square law model, so what we now do is, we are trying to generate an equation, and that equation is going to be this. So we are trying to take this equation. From this equation we have extracted multiple components, and we discard the first component, discard the second component, we discard all the other components, and we retain only this, this and this. And how are you going to get these components now? These components are basically obtained by again passing the entire data through a filter. So it's basically a low pass filter. So what happens? Because it's a low pass filter and the cutoff frequency low pass filter will be set so that it can only filter off m of t. All the other signals are going to be removed. So if you see, what is going to happen here is, there are three components which are primary importance for us. The first component is VDC, second component is this, third component is this. But out of all the three components, this component is of more importance for us because it is going to have message. Because it is going to have message, what we now do is, we are trying to take the signal and pass the signal through a low pass filter. When you pass the signal through a low pass filter, what happens? Along with this signal, we also get two more components, which are the DC components available within the carrier modulated data, and that is what we call it as a square law demodulator. Okay, yes. Okay. Now let us understand the another very interesting technique called as the synchronous or coherent demodulation. It's a very interesting thing now which we had actually discussed earlier itself, but let me now try to make you understand what is the importance of synchronous or coherent demodulation. Yes, let me quickly go back and summarize. So as we were discussing, there are two kinds of modulation techniques: envelope detection and synchronous detection. In envelope detection, there are two methods, two different techniques to be understood. One is based upon the diode envelope detection logic. The second one is basically based upon your square law model. In both the models, what is going to happen here is, the signal that is coming from the channel is directly fed into a demodulator. The diode and the corresponding resistors and capacitors are able to extract the message. But what happens in synchronized demodulation technique is, in the synchronized demodulation technique, what we actually do is, your input signal AM of AM input is now applied and it is multiplied by a local oscillator, and then the output of the local oscillator, which is now represented by Vx, is given as an input to a low pass filter, and we get output m of t. The reason why we do in this way is basically this. Yes. So we know that m of t is your m of t is your message signal. We are multiplying m of t with your carrier signal cos of omega ct. This is what is a signal that is basically transmitted. Once we try to take the signal m of t cos of omega c and it is being transmitted, at the receiver your m of t cos of omega ct is further multiplied by cos of omega ct. So what happens? This is the transmitted data, and this transmitted data is now multiplied by cos of omega ct. So when you try to take m of t cos of omega ct and multiply it with cos of omega ct, you get m of t into cos square omega ct. Now this cos square omega ct is obtained because you are multiplying m of t cos of omega ct by the same carrier at the receiver, that is cos of omega ct. We know that cos square omega ct is now equal to 1 plus cos of 2 omega ct by 2. So if you multiply this entire data with m of t, if you multiply it with m of t, we find that you get back your m of t available here. And that is the technique that is used in your demodulation process, and that is your synchronized demodulation technique. So what is being done in synchronized demodulation technique is as follows. Yes. So we are trying to take your AM signal which is coming from the channel. This AM signal is now multiplied by a local oscillator signal, which is again going to be cos of omega ct. By multiplying AM signal with cos of omega ct, we know that you are able to split m of t from the carrier. Because you are able to split m of t from the carrier, and m of t is always said to be a low frequency signal. So if at all you pass it through a low pass filter, your low pass filter will remove all the high frequency components and retain only the low frequency components, and you will be able to get m of t at the output. And that is what basically happens in synchronous coherent demodulation technique. But why do we call it as synchronous coherent or coherent demodulation technique? It is called as synchronous or coherent demodulation technique basically because if at all you take the local oscillator signal at the carrier, and if this local oscillator signal at the carrier is not exactly matching with respect to the frequency and phase of the incoming carrier signal, what would happen is you will completely lose the information. Because of the multiplication process, what would happen is, okay, there will be lots of deviations occurring, and the entire information would get lost. To ensure that error doesn't occur in the demodulation process, what we now do is, whenever your AM signal is now received, if your AM signal is being received, from the AM signal what we do is, we take this signal and give it through a band pass filter. Now it's a very interesting technique that is basically being done here. If your AM signal is given to a band pass filter, okay, and if the band pass filter is set to a cutoff frequency such that it is able to filter off only the frequency FC. So if at all your signal, AM signal is anything, but if at all it is passed to band pass filter, the band pass filter will allow the frequency components only in the frequency range FC. All other frequencies will be removed by the band pass filter. Because all other frequencies are removed by the band pass filter, only the frequencies that are in the range of FC are now allowed through the band pass filter. The output that you get here is only going to be the carrier signal, and that is what we call as LO. So the signal what we get here is cos of omega ct. So what is actually done here is, instead of using a separate local oscillator to generate the carrier at the receiver, what is the technique that is adopted? We use a band pass filter, and this band pass filter is going to only allow the frequencies that are within FC. So output of a band pass filter will always have a carrier signal of cos of omega ct. So what we now do is, this cos of omega ct that is extracted from the band pass filter is now used as the local oscillator signal, and we multiply it with the AM signal, so that there will, even if there is any deviation in the AM signal, same deviations are also going to occur in this local oscillator signal, and then you will be exactly able to reproduce your m of t from the input signal. And that is why we call it as synchronous or coherent demodulation technique. The reason why it is called synchronous is because the local oscillator frequency at the receiver is synchronized with respect to AM signal here, and that synchronization is achieved because of using a band pass filter. this band pass filter will ensure that the incoming signal will be completely only allowing a carrier signal FC, and that signal will be in line, in synchronous with your AM signal, and if you multiply these two of them, you will be able to get back output, and if you pass it to low pass filter, you will be able to get back M of t, and that is the advantage of having a synchronous coherent demodulation technique. Let us understand these concepts mathematically. Okay, yeah. So what is happening here is, we are assuming now the local oscillator frequency which is now going to be generated is actually extracted from the AM signal itself. Now if you assume that the local oscillator frequency and the carrier frequency here, both of them are identical. Okay. Now if by multiplying VDC plus M of t cos of omega ct into cos of omega ct, you find that you get a mathematical equation which is VDC plus M of t into cos square omega ct. Now we know that cos square omega ct is 1 plus 1 by 2 plus 1 by 2 cos of 2 omega ct, and further multiplying this, we have three components: the first component, second component, third component, and fourth component. All the four components are now available. Out of all the four components, this component is of primary importance for us because it consists of information, and all the other components are removed. So how do we remove it? By passing the signal through a low pass filter, all the high frequency components are automatically removed, and we get back only M of t. Now the advantage of this is, even if there is any deviations occurring, whatever signal is basically used for the carrier, the same carrier signal is now used at the receiver to get back your modulating data, and that is why we call it as coherent or synchronous demodulator. Okay, yes. Okay. Now let us summarize. So to extract message from your demodulated, extract message from your modulating signal, there are two methods that are available. One is called the square law demodulator or synchronous demodulator. Square law demodulator is also called as envelope detector. Okay, this is what we need to be well versed with your AM demodulation techniques. Okay, let us quickly review. Suppose what all you would like to understand what are the techniques that we have discussed till date. Okay, now some of the important questions or some of the important parameters that we may have to understand is, why modulation technique and what are the types of modulation technique. Okay, so if at all somebody asks you why modulation, I discussed the modulation technique is basically because of various reasons. One is the length of the antenna is going to be reduced. Second thing is, you can have multiple channels. You can ensure that you instead of broad wideband, you can go for narrow banding. Plus it will ensure that there is no loss of data. So all this information is going to tell us why we need to go for modulation. Then there are three kinds of modulation that we discussed: amplitude modulation, frequency modulation, and phase modulation. In amplitude modulation, we have discussed there is a concept called modulation depth, and that modulation depth, okay, if it is less than 1 or if it is equal to 1, we are going to get double sideband signal. Suppose if you make it more than 1, then it is going to be double sideband suppressed carrier. And if your modulation, if you are taking your modulation double sideband suppressed carrier and you pass it through a frequency or you pass it through a low pass filter, you will be able to remove one of the subbands and you will be able to have single sideband and it will be suppressed carrier. So these are the various AM techniques. So we have not discussed your double sideband suppressed carrier and single sideband suppressed carrier, but we have just concentrated on double sideband AM signal. Then we also discussed what is the power of an AM signal. Then we also discussed what are the demodulation techniques available. So there are two demodulation techniques. One is non-coherent, the other one is coherent demodulation technique. And this is how we have summarized amplitude modulation signal. Now let us go to the next important concept, that is frequency modulation. Okay, so let us very quickly understand what is frequency modulation. Okay, yeah. In frequency, before we could get into the concept of frequency modulation, let us now understand what are the limitations of AM, why we should be able to go for FM. Okay, the limitations of AM are as follows. The AM signal is greatly affected by noise. Now it's a very interesting demerit of an AM signal. Why is that? So what happens is, if at all you try to take an AM signal, and if your AM signal is so and so, where we are able to see an AM signal. So if at all you have a noise available in the channel, and if the noise available in the channel is basically a peak or a pulse, okay, assume that there is a noise available in the channel, or there's a small amount of noise available in the channel, or there's a small amount of noise available in the channel like this. These are all the noise that is available in the channel. If this noise frequency, okay, if the noise frequency matches with the carrier frequency, this is the carrier frequency now. So what would happen is, if this noise frequency matches with the carrier frequency, now what happens? It will actually have an additive role. That means this frequency will get added, or this noise will get added to the carrier signal, and instead of having this peak, your peak will be getting increased by this factor. So if your channel consists of a noise, and if the noise frequency is exactly matching the carrier frequency, what happens? There is a addition happening. The noise gets added onto your AM signal. When the noise gets added onto your AM signal, what would happen is, because the noise frequency is exactly matching with the carrier frequency, you find that there is a increase in the signal strength here. Now because of the increase in signal strength here, the peak of your AM signal will be now changed. So instead of having a peak, let me change the color here. This is the actual peak of your AM signal, but because of the noise that is available in your channel, and that noise frequency is basically matching the carrier frequency, the peak of your AM signal will be changed. So you find that the peak of your AM signal has been now changed like to this. So let me first repeat it. This is the peak of your AM signal, okay. But what would happen basically is, because of a noise available, and that noise has the frequency exactly matching the carrier signal, a noise will get added here, and the envelope of your AM signal will be now this. So what is happening? It affects the amplitude of an AM signal after when you do demodulation process, and that is why we tell that AM signal is greatly affected by noise. We know that noise will be available in all the frequency range. So why noise will be noise will be present from 0 to infinite frequencies. So whatever carrier you try to use, definitely there will be a noise which is going to match with the carrier frequency, and that will be basically affecting the peak of your signal. And that is why, okay, your AM signal may get distorted, and it will be difficult for us to remove the AM signal, remove the noise from the demodulated AM signal. And that is the reason why there is a huge drawback for AM signal. Second important thing is, impossible to determine absolutely the original signal level. So the reason is, okay, because of this noise factor affecting here, and there may be multiple noise factor affecting here, so there will be multiple noise, we may not know which is the actual signal is, because the signal is, because this is the actual signal, but because of noise your signal may be like this, your signal may become like this. So there are two signals available. The actual one is at the bottom, the top one is this. So what happens, we will not be able to really from the demodulated data, we will not be able to really know which is the actual signal. So it will be very, very difficult for us to understand which is the absolute signal which is going to be demodulated. Okay, that is the second demerit of your AM signal. Conventional AM is not efficient in the use of transmitted power. The reason is, if at all you try to transmit the signal, we know that the total power required is the carrier power multiplied by 1 plus m square by 2. So for transmitting an AM signal, okay, you need to have large amount of power. That is another limitations of AM signal. Similarly, AM signal is useful where a simple low cost receiver and detector is desired. So whenever you try to you want to go for AM modulation, you prefer to use AM only whenever your detector is going to be very, very simple. Okay, because you need to have a diode, you need to have a resistor, you need to have a capacitor. If at all you want to reduce the cost of the receiver, only at that places we go for AM modulation. But the limitations of AM modulation are, one is it will be greatly affected by noise, and it will be not possible for us to exactly extract the absolute information from the AM signal. Thirdly, okay, the power required for transmitting AM signal is going to be very large, and the advantages of AM signal is it will always use low cost receiver. Okay, so that is the advantage of your AM signal and limitations of AM signals. Okay, yes. Yeah. Let us now understand the meaning of angle modulation. Okay. So, angle modulation is called because there are two factors involved in this process. The two factors are, one is frequency modulation, the other one is phase modulation. So, here both these modulation are now classified under a category called angle modulation. See, earlier it was amplitude modulation, now we are talking about angle modulation. Now, in angle modulation what is going to happen is, the intelligence of the modulating signal can be conveyed by varying the frequency or phase of the carrier signal, and that is what we call it as angle modulation. So, that is the instantaneous amplitude of the modulating signal, that is message, is now going to either change the frequency of the carrier or it is going to change the phase of the carrier, and that is how we call it as angle modulation. If the modulating signal is going to affect the frequency of the carrier, we call it as frequency modulation. If the modulating signal is going to affect the phase of the carrier, we call it as phase modulation. So, in 1936, Major Edwin E. Armstrong has coined the word called frequency modulation, okay, and he has identified that because of frequency modulation, okay, you are able to overcome all the demerits of amplitude modulation, and it was very predominantly used, and even today frequency modulation is used in many of the techniques. Okay, now if you try to see, frequency modulation is used in television, frequency modulation is used in commercial FM broadcasting, frequency modulation is used in paging system, frequency modulation is used in cordless telephony. So, there are multiple applications of FM modulation. FM is basically used, the reason is it is immune to noise that is available in the channel, and that is the only advantage of using FM, and it is predominantly used for all possible applications. Okay. Now, let us understand what is frequency modulation is. So, before we could go to the next slide, so let us understand, if at all the modulating signal is going to affect the frequency of the carrier, we call it as frequency modulation. And frequency modulation was basically identified or invented by a person by name Major Edwin E. Armstrong in 1936, and he invented this to overcome all the limitations of AM signal. And it is also found out that FM modulation or frequency modulation is immune to noise available in the channel. Now, let us understand in detail what is frequency modulation and what is phase modulation. So, let us define what is frequency modulation. The carrier's instantaneous frequency deviation from its unmodulated value varies in proportion to the instantaneous amplitude of the modulating signal, and that is the basic definition of frequency modulation. That is, let me now illustrate it with a simple graph here. So, what is happening here is, the instantaneous amplitudes of the carrier or the modulating signal is now going to change the frequency of the carrier. So, if the magnitude is slowly increasing, the frequency is going to increase and then it is going to reduce. So, the frequency, the amplitude of the carrier is going to remain same. The carrier will have the constant amplitude, only the frequency is going to deviate. The frequency is going to increase or it is going to reduce depending upon the strength of the modulating signal, and that is what we call it as frequency modulation. It is mathematically represented by this equation. There are two expressions, either I can use a sine or I can use a cos. And if you take the second expression, it is AC cos of omega Ct plus m of sine of omega mt, where sine of omega mt represents the modulating signal, cos of omega Ct represents the carrier signal. We are now trying to change the carrier frequency by modulating frequency. So, this parameter over here is now going to define what is frequency modulation. Okay. Similarly, let us also define what is phase modulation. Yes, in phase modulation what happens basically is, the carrier frequency will remain constant, the carrier frequency will remain, amplitude will remain constant, but the peaks of the modulating signal, that is the peaks of the modulating signal will affect the phase of the carrier. Because the phase of the carrier is being affected, the frequency also gets affected in a phase modulated signal. That is, the carrier's instantaneous phase deviation from its unmodulated value varies as a function of the instantaneous amplitude of the modulating signal, and that is the definition of phase modulation. Okay. So, let me summarize. In phase modulation, the modulating signal sine of omega mt changes the phase of the carrier, and that is what we call as phase modulation. Let us stop here and continue the discussion with the brick. Okay, na?